what we did in some of the previous lecture, I try to resume. We have the least action principle. Okay, you can find the complete calculations for deducing the first variation of action functional for a continuous body, first or second gradient, in the paper I gave you of Frey et al. Okay? In this paper, Mathematics and Mechanics of Solids 2014. Okay? In this paper you find all calculations very carefully written. When it was too much, I wrote in the appendix. Okay? I wanted to, the original result there was a certain Lagrangian formulation for second gradient fluids. However, I exploited all the procedure, all the calculations I needed for presenting in a clean, self-consistent way the theory of least action first principles for the calculation of first variation of action and its equating it to zero and finding strong conditions which are implied by the equality to zero of action. Okay. In this paper, you will find the derivative. Among the others, you will find this equation. Derivative of this plus divergence of pure stress equal external forces and the relative boundary conditions. Okay? So you will find the balance equation for force in the Lagrangian configuration, including inertia terms, plus the relative boundary conditions. These are the Euler Lagrange conditions which are relative to the action for a first gradient continuum. Okay? In another lecture, we started from a Lagrangian depending on Q dot, and T, where Q are the n Lagrange parameters of a model having finite dimensions. And we wrote the action as the integral of this Lagrangian function. Okay. So this was the action. We calculated the first variation of action. We equated it to zero. These calculations I have done. You have the video recorded lecture about this. And after few integration by parts, we found for isochronous, so delta Q has to be zero at T0 and at Tf. Okay? You find Euler Lagrange equations having, if you remember, this form. And there are many of these equations. How many? Exactly how many degrees of freedom you have. So I is equal 1 to up to n. Okay? So you get as many equations, as many unknown functions you have at the beginning. This is the beauty of variational principles. You get always exactly the number of equations and boundary conditions which you need. Okay? Now, this is the equation for a continuous body. That one is the equation for a finite dimensional model. This one is a model, infinite dimensional. So I'm repeating for you something which we already discussed. Okay? Good. Now, using finite elements, you can reduce the problem of minimum of action for a continuous body, the problem of finding the minimum of action for a discrete finite dimensional system. So, instead of solving this, you solve that system. So what you are doing, you are reducing a problem in which the unknown field is the placement field to a problem in which you have a finite number of real numbers. So you have A1, A2, AN parameters which are characterizing your displacement. This is what is done by COMSOL. COMSOL is doing this. COMSOL is. I want to repeat for you once more this because you will never be able to use COMSOL if you don't understand it. So my action is integral P0 to final, integral over C star, the reference configuration of 1/2 rho V square minus W of F if we are working with first grade materials. Okay. Then you have minus B dot key if you have volume forces B. Okay. And then you have plus integral over the boundary of C of minus of F external dot key.
Sorry? At the boundary or only?
Boundary. I said boundary and I didn't write. Okay? So what you have? You have kinetic energy. Then you have deformation energy of first grade. So this is the energy you are storing in the deformation of your body. Okay? Then you have the potential energy related to the displacement of one material particle of your body from one position to another position. And then you have contact forces. So the boundary of this body is moving, and because of the external action, force per unit area applied to the boundary, you have another possible potential energy. Of course, we can add springs, we can increase the complexity of your model, but for a moment, let us try to attack the simplest one. Okay? Now, you have a difference. Here, you have integral of sounding, which via q dot depends on time and explicitly depends on time. You have no volume integral. Okay. Here, you have also a volume integral. Okay. What we do? We take the volume C star. This is what you are doing with constant. You take your volume C star. Okay? You cut it into pieces. Each piece is a finite element. Now, I will not be more specific about the nature of the pieces. You have seen, I think that Ivan has shown you that you can choose cubic finite elements, tetrahedra, and there are many different kinds of decomposition of your system. So what you have to do is the following. You take C star, you partition it. In mathematics, a partitioning is a precise decomposition of a given set. So C is equal to the union of Ci, I goes from 1 to n, okay. Or if you want to use a more sophisticated way of indexing, you can introduce 3 indices, one for every coordinate axis which you are using for decomposing this element, because you could have the cube in the position I, j, k, I along x, j along y, k along z, zeta, okay? It doesn't matter. You have a finite number of subset of C star, having also the beautiful characteristic that Ci intersection Cj is empty when I is different from j. So you have to be careful with the boundaries. Okay? This is what mathematicians call a partition. Okay? So you have a given family of subsets of C star, and the union of these subsets is giving you C star, and the intersection of this, every day of this subset is empty. Okay? This is what is called a partition. Then what you do? You assume that the unknown function k, when x belongs to Ci, is given in terms of a1i dot aki. So one could be general enough and say that the number of parameters which you need to specify in the Ci element of partition, of your partition, this depends on a number of parameters which is varying. So, for instance, here you use 6 parameters, here you use 7 parameters, here you use 20 parameters, here you use 3 parameters, depending on your choice. Okay? And this we can represent adding an index k of I. So the number of free parameters you are introducing in every finite element depends on the particular element you are considering. This could seem to you another useless general statement. Okay? But it is not true, because when you need to study problems and you know that here something strange is happening, while you are rather sure that here nothing strange is happening, you could decide that your finite elements here are full of parameters and your finite elements here are with less number of parameters, and this could make your numerical simulation quicker, because you are not wasting your time in these useless calculations. I like very much to make an example which I use in some philosophical discussions, sometimes involving my mother. Mothers want to be clean, so they want to kill all bacteria, all viruses. Okay. However, there is a maximum possible. You cannot kill everything. So you know that a given amount of cleaning soap or disinfecting gel, rubbing it a number of times, kills 99.9% of bacteria. If you do more, it is useless, because bacteria are around us, and even if you rub more and more, you don't manage to kill more than all bacteria you already killed, because they are falling on your hands via air or vapor or air. I'm sure that you have seen surgeons in a movie cleaning themselves 7 times, scratching away the more superficial layers of their skin. You do it more than 7 times, it is useless. So if you are a surgeon, you must be disinfected at a given level, and you wash your hands half an hour. If you are preparing a pizza, knowing that it will go in the oven where you have 700 degrees, and this pizza will remain there 2 minutes, you will have your hands clean, of course. You will not scratch the layers of skin in a useless way. Okay? For being a pizza maker. By the way, it is dangerous, because he is not transmitting to you diseases, but with hands scratched, he will open his body to the attack of external agents. So it is something either useless or dangerous. Okay? Let us go out of the metaphor. Okay? If I want to be precise, and I introduce 1 million parameters for every finite element, I will get a wonderful picture of every phenomenon. But my computer will never give me the result, because he has to do too many calculations. So a clever strategy is to choose the finite elements, to be rich enough where they are useful. So this would be the corresponding of cleaning the hands of a surgeon, and you can be a little bit lazier in other situations, and so you have less parameters introduced in another finite element. So these symbols are very important. Of course, if you have one finite element here, okay, and you move to the closed finite element, you do not want that the displacement here is discontinuous. Because discontinuous displacement field gives you a lot of troubles. You need the gradient of displacement in order to calculate energy. If you have a jump of displacement, you have a derivative somewhere which is infinite. I don't know if you have this in mind. So let's stop talking about this a little bit. If I have this function, which is perfectly smooth, here the derivative is 0. Here the derivative is nearly 0. However, here the derivative is very large. However, this derivative is finite. When you change this slope in the limit, you will get something, a Heaviside function, showing you this. Here, you have a jump of displacement, which is the limit. This is the limit of a sequence of functions having a slope higher and higher, tending to infinity. So when you have jumps of displacement, you have troubles, because you have a gradient somewhere which goes to infinity, and you cannot estimate this energy. Or you can have serious troubles in estimating this energy. We already spoke about this. We said we want to study the deformation of a body which is behaving in a reasonable way. So we don't have epsilon cubes which are crunching. We don't have epsilon cube which are becoming very large. So we have nearly everywhere the gradient of displacement. This gradient is continuous. So if your finite elements are chosen in a bad way, not wise way, so if in this element you have a displacement, in this other element you have another displacement, Ki and Ki plus 1, you have another displacement, and you get a discontinuity, you are in troubles. Because your tentative solution is not respecting the kinematic assumptions you have accepted at the beginning of all the story. Okay? So these parameters are not all free. This makes the theory of finite elements different. These parameters must be chosen in such a way that the displacement is continuous, that the first derivative of the displacement is continuous. Okay? Now you understand why people are having troubles to study second gradient materials. A finite element which is very good for first gradient continua, because the polynomial in every cell is well behaving, and you have glued in a very wise way the derivatives of these finite elements at every boundary. This bad boy could have a gradient of f which is discontinuous. So a finite element which is very good for Cauchy theory can be, first gradient theory, can be very bad for second gradient continuum. Because you have a gradient of f, which for your finite elements is absolutely meaningless. Okay? Do you know why second gradient theory was not accepted for nearly 50 years? Those people were so attached, morbidly attached to the integration scheme, which is good for first gradient continuum, that they applied it also for second gradient continuum polynomial. They found absolutely meaningless results. Instead of asking themselves the question, where my hypotheses were not suitable, they preferred to say that second gradient continuum are not existing. This is a typical attitude of human beings. Square root of 2 is not rational, it is not existing. Ptolemy was trying to discuss about some far islands which were out of every known longitude. Instead of suspecting that some Greek could reach these islands, they said the longitude was wrong. Do you like some grapes which you don't manage to reach? Do you know the famous tale of Aesopus? At the end, and now I remember in French, Renard, I will find the name in English. The animal who wanted to eat the grapes tried to jump to it. He didn't manage, and then he said, okay, I don't like these grapes. They are not good enough. I will leave them. If you have troubles, it means that your finite elements are not good enough. So you need to adapt your finite element scheme to study more complicated models. The beauty of CONSOL is that this adaptation can be done easily. So you can change the finite element in order to be able to deal with more complicated, non-standard models. Okay. Let us continue for a while to discuss about first gradient materials so we can understand what we are doing now. Okay? What we do now? We have chosen a function k, which is piecewise polynomial. So in every element ci, this function, which I've called ki, is a polynomial on x with respect to the x variables. Okay? Now I have a trivial question for you. If you need first derivatives, linear polynomials are good because their derivative is not trivial. It is constant, but it is not trivial. If you have second gradient materials, the second derivative of a polynomial of first order is 0. You become blind if you consider first order polynomial approximation, and you have an energy of second gradient. You don't see the second gradient, see? Because your polynomials are too simple. So a wise man will consider at least second order polynomials if he wants to study second gradient materials. Okay? So what I'm telling you now is very important for choosing the correct finite element in a given problem. Okay. So what you can do? Integral over C star, you can split integral over C star of what is there plus integral over the boundary of C star what is there can be written as sum over I of integral over Ci of the same minimum here. Okay? Then you must be patient and you must cut so-called boundary elements. So when you are here, if this is your potato C star, when you are here on the boundary, you must consider this animal having some sides which are well behaving and one side which is cut by the boundary you have. Okay? Or you have to do what is called a rectification of the boundary. You can decide that your boundary is like that. You have the pixels of your finite element and you reconstruct a complicated boundary with some piecewise flat boundary. Believe me, if you want to build a software recognizing the fingerprints, you need to develop carefully this kind of pattern recognition and finite element. Okay? Good. So we call integral on the first, the summation is over another index. We call it h from one to another n bar, integral of the boundary CB h of this other animal. This is a standard position. When you are an integral, you can always write Riemann sum approximating that integral. And in your Riemann sum now, you are considering Ci and C boundary. Okay. Now, in each of these Ci, your unknown function Ki is a polynomial in X in terms of some finite number of indices, of parameters. Okay? So, you can calculate its derivative with respect to time, because these parameters are the only one which depend on time. You can calculate the gradient, you will get a lower order polynomial. can integrate the polynomial with respect to the x variable. You can calculate b dot a polynomial and f dot a polynomial. So which is the structure of each of these integrals? You have integral over the domain Ci of what? A0 plus A1x1 plus A2x2 plus A3x3 plus all the other polynomials which are there. So you will have, I don't know, A1, 2, x1, x2, and so on. Okay? You know how to calculate this integral. Because A0 integral over Ci is the volume of Ci. A1x, you can calculate the integral of x1 over a volume. And A1 comes out. So you understand that each of these integrals is computable. Each of these integral is computable. Okay? When you calculate the derivative with respect to time of this animal, you get A dot, A1 dot, A2 dot, A3 dot, A1, 2 dot. So you can place it here. You multiply times the density, and you get something which depends on A0 dot, A1 dot, An dot. We have understood what we have done. We have taken the action function for an infinite dimensional system. In our case, it was a first gradient continuum, and after some assumptions about the displacement function we want to use, instead of using a more general one, we have used a polynomial, piecewise polynomial, depending on some parameters. We have done some calculations, and at the end of the whole story, we get this pattern, where Lagrange coefficients are the coefficients of the polynomials we have introduced for every finite element. Now, it is not a casual circumstance that some of these polynomials are called Lagrange polynomials because they were invented by Lagrange in a very similar context. But you can have Hermite functions. You can have polynomials with a free point called Gauss point. You can have many possible, conceivable, useful Ki polynomials. Each of these polynomials will characterize a new finite element. There are many finite elements. Each finite element is suitable for a specific application. But the general procedure is always the same. You take this polynomial, there is no reason for having polynomials. You could have another function. The important thing is that you manage to calculate these integrals. In general, finite elements are expressed in terms of polynomials. You take these polynomials, You plug in this first external integral. So internal integral, the one on the Lagrangian configuration and on its boundary. You do all calculations you can perform by exploiting the structure of Ki as polynomials. And at the end of the story, you get a Lagrangian which depends on Q of M. The good news is that this Lagrangian finite dimensional model has an Euler-Lagrange condition, which is an ordinary differential equation, which in general has a unique solution. And this unique solution can be computed. So, once we have chosen suitably finite elements, then you reduce an infinite dimensional system to a finite dimensional system. Okay. Now, what we want to do, maybe we stop after some beginning of this discussion, we will conclude it tomorrow, in order to dilute what I'm telling you. Now, what happens is that this Lagrangian can be studied in some particular cases in a very effective way. And if your choice of finite elements has been wise, the solution which you get is very close to the correct solution. And if your model is good, which happens very often, you have got the correct approximation of the solution of your problem, so you can forecast what happens to your system. Okay. So, let us look a little bit to Lagrange equations for a finite dimensional system. What is an equilibrium solution for this system? An equilibrium solution is a solution in which Lagrange parameters are not depending on time. Equilibrium means that motion is rest. So, Q of t equal Q0 has to be the solution of our system. Okay? Okay, I hope that you are now familiar enough. This is the reason for which I decided to split into this part of our discussion. Do you remember somebody came to show me an integration of a composed function? So, yeah, this element here must be calculated with that scheme. So let's do it slowly. Okay? So you have dl over dqi, And this animal depends on Q1, Q2, Qn, Q dot 1, Q dot n. Okay? And each of these variables depends itself on time. When I try to calculate this derivative with respect to time, what I have to do? I have to calculate dl over dqi dq1. So the derivative with respect to the first variable. Then I have to calculate the derivative with respect to time of the function q1. So here I have q dot 1. Okay? You agree? This is the derivative of composed functions. But I have also q2, qn. So this becomes dot 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 dl over dqi dqn q dot n. So I have calculated the derivatives of this group of variables. Okay? They are not ended. I have also plus the derivative with respect to qi, q dot 1, q double dot 1, which is obtained by calculating this derivative with respect to time. Okay. And then I have plus dot 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 dl over dqi dq dot n q double dot n. Of course I am lazy. I don't want to write all these complicated functions, sums. So I can resume this as follows. Look at that formula in that corner. The quick version of this formula is this one. Sum over repeated indices. Okay? So this is meaning exactly what I have written before. This is simply a quicker way. There is no difference. Okay? Okay, why this is very important in our context? The motion, D'Alembert understood many things. One of the most important things he understood is that motion remaining at rest is a particular motion. Motion is a function which to every instant t associates the position of your system in the instantive. Remaining always in the same configuration is a particular motion. I know this is trivial if you think in the right way. However, it was an intellectual discovery. So, the principle of least action implies that motion is solution of this equation. To assume that a configuration is an equilibrium configuration implies that the function qt equal q0 is a solution of your equation of motion. This is another trivial thing. Okay? Now we have calculated this derivative. Okay? This derivative is written here. Okay? Which is the first derivative of a constant? 0. Which is the second derivative of a constant? 0. So all these derivatives are 0. So necessary and sufficient condition for having that Q0 is an equilibrium configuration of your system is that dl over dqi calculated in Q0 is equal to 0. Tell to everyone. In English.
This diagonal should be 2 dots over the qi and qj.
Where? Here. You mean here?
Yeah.
No. Because L is a function of Q1, Q2, Qn, Q dot 1, Q dot 2, Q dot N. Here is you mean here? Yes. Yeah. I wrote the good one. I've written only for the first one and then yeah. So tell it. This is, and I forgot here. This is the L over dq. And then I must calculate the partial derivative with respect to Q1, Q2, Q dot 1, Q dot 2. So I misunderstood your question. Because I believe that you don't have 2 dots here. You want 1 dot here and 1 dot here, which is 2. And here you have 1 dot and here without the dot. And the dot is there. And here you have double dot because you calculate the derivative of the first derivative, so you get second derivative. Okay? Good. So let's repeat what I said. Q of t equal Q0. The first derivative of this animal is 0. The second derivative of this animal is 0. Therefore, this derivative is 0. So this animal is 0. This derivative is 0, and therefore all these animals are 0. So in equilibrium. So in equilibrium, dl over dqi Q0 is equal to 0. So an equilibrium condition is such that the first derivative of the Lagrangian with respect to the Lagrangian variable have to be, all of them have to be 0. So this is a necessary and sufficient condition for equilibrium. Okay. Now, before stopping, let us have an overview of what we have to do next time. This you should have already done for the study of the pendulum. So let us, this is a problem solved by Galileo. Okay. If you have a mass, here you have a suspension point, and this mass is moving with this distance always kept the same. Okay? I give you an exercise. If this is theta, this is L, this is L, okay, the length. I need to calculate this angle in terms of theta. Okay? So you know L, you know theta. This is a trivial exercise in trigonometry. Why this angle is very important? Because this is the variation of height with respect to this zero. So gravitational potential energy depends on this difference. Okay? The Lagrangian of the pendulum is equal to 1/2 mass velocity squared. Okay? Another exercise I give to you is to find this velocity in terms of theta dot, okay, minus the potential energy U of phi, theta, okay? Now, what Galileo understood, if you have a small motion in the neighborhood of the vertical equilibrium configuration, every sinus theta is nearly equal to theta. Every cosinus theta is nearly equal to 1. And you can get a beautiful quadratic Lagrangian, which after the derivation needed for getting all the Lagrangian equations is transformed into a beautiful linear differential equation. What is doing Galileo is finding the equation of the small motion in the neighborhood of an equilibrium condition, linearizing the equation of motion. Now, why this fixation? Because linear equations can be solved sometimes. by hand. So I give you another exercise. It is you should already have done it. If not, you find in Wikipedia. I mean, it is very easy, but think about this because tomorrow we will need to do this in detail. And what Ivan is showing you is a similar position. The small motion close to a reference equilibrium configuration. What you have is that mass, a coefficient J, theta double plus another coefficient theta equals 0. Find the coefficient J and K. This is the equation which is valid when theta is very small. So when you can develop in Taylor series truncating the expansion at the first order in the neighborhood of theta equals 0. This is the equation of harmonic motion, whose solution you have already seen, I am sure. Now, consider the complex structure which Ivan needed to study. Consider one equilibrium configuration. We want to study what happens if you pull it, push it, displace it a little bit, and you have small motions around that equilibrium configuration. So we need to generalize Galileo process, the one which we used for the pendulum. So what we have to do? We have to linearize Euler-Lagrange equations in the neighborhood of an equilibrium condition for finding the most general equations of small motions. Okay? They are called the equations of small motions. Now, many times I have heard by engineers that these equations of small motions are the only practical ones. I mean, okay. So they claim it is useless to talk about general equations of Euler. And they tell you always the same story. Practically, in practical applications, practical engineers need practically only when somebody repeats you practical too many times, you must become suspicious. He doesn't know what he's doing, and for justifying it, it says practical, practically, in practice. Okay? Now, as usual, it is the other way around. We do not know how to solve by hands nonlinear equations. So even if we tried nonlinear equations before COMSOL, we looked at them and we said, oh, beautiful. And then we stopped without knowing how to solve them. Instead, we know very well how to solve linear equations. So what we did? We built only systems which move very close to an equilibrium configuration. So it is an a priori choice. Do you want to build a bridge? You must build your bridge in such a way that it has an equilibrium configuration, and whatever you apply to it, and of course you have to imagine that the maximum wind is of a given intensity. The maximum load applied is of a given intensity. I mean, you need to know which kind of external actions you apply to that bridge, and then you must calculate a priori that every externally applied action is not moving your system too far from the equilibrium condition. So the equation of the pendulum are not valid if you take your pendulum and you place it here. This angle is not small. You don't try to apply these equations in this situation. You apply these equations only if you are close. So you take your bridge, you know a priori that this bridge is subjected to a given family of loads. You calculate all equilibrium conditions under these loads, and you know that you are very close to a given load. Then you feel confident and you linearize your equations. Okay? Now, what will happen in your bridge? Your bridge will be much, much stronger than strictly necessary. Okay? You are over-dimensioning the bridge. I mean, you are building it many times stronger than what is strictly necessary. Nothing but you are not optimizing your design. Why you are not optimizing your design? Because you are ignorant. You do not know how to solve non-linear equations. You have seen the wings of the airplane. They are moving a lot. Why? Because you need to exploit their resistance, mechanical resistance, a lot if you want to optimize the ratio weight resistance. You can build a wing very resistant, which is not deformed under the aerodynamical laws. If you do this, what will happen to your airplane? It will never take off. It is too heavy. You cannot decide that you are always in linear regimes changing this parameter, for instance, or this one, in order to have linearized the equations which are not. So it is not true that practically you need only linear equations. You can solve only linear equations easily. So, in many situations, we prefer to use linear approximations. Okay? So, what I want to teach you is how to generalize Galileo treatment of small motion of a pendulum to an n-dimensional mechanical system, which is the output, as we have seen, to every finite element scheme for an infinite dimensional system. Okay? So, in a sense, we will write the equations of everything, Euler-Lagrange equations. We will apply the hypothesis of small motion in the neighborhood of an equilibrium configuration, and we will see what we can do in general for small motions. Okay? And you can tell to your colleagues in Italy who claim that linear algebra is useless nowadays for engineers, and small motion in the neighborhood of equilibrium condition cannot be studied without linear algebra. Delegation of your colleagues came to me to say, nowadays linear algebra is not useful for engineers. I said, I know, nowadays a brain is useless for engineers. So you can cut away 1 hour of your brain, it is useless. I mean, how can you believe that you can live without linear algebra? Solving linear system of equations. They are the simplest one, or another. Okay? So you will see that linear algebra is very good. But then, okay, so let us